Okay, so in the last video, we introduced this idea of conjugates, which was an algebraic way of saying sort of all roots are the same algebraically. And we're going to make that even more precise now. So we're going to show that, we're going to show how to take quotients of the polynomial ring and on the way give an algebraic statement and proof of the fact that sort of all roots are the same algebraically, which I'll point out when we get to it. Okay, in the meantime, let me just observe that this K join T is a PID. Okay, so if you're going to take quotients of a ring, you look at ideals, left or right ideals. This is a commutative ring, so we only have to say ideal. And in a PID, all ideals are principally generated. So all of the ideals here are just generated by a single polynomial. So any ideal is principally generated by some single polynomial. Oops. All right. So a lot like when you take the integers and you quotient by a single natural number, we're going to take the polynomial ring and we're going to quotient by a single m of t. And this is the analog of those. And these are the only types of quotients. Okay, and that's my purpose. That's the purpose of me saying this. If you don't really remember principally generated ideal or principal ideal domains, that's okay. We're not really going to need any of the ring theory, but we will go over the construction of how you do arithmetic here. So we're going to fix at the outset some m. I'm going to really emphasize that these are polynomials, but you don't have to write the of t if you don't want. So we're fixing a polynomial. This is like the modulus. Right? So let's underline that. Okay, so we're going to define a congruence relation. Congruence modulo m by a of t is congruent to b of t modulo m if b of t minus a of t is divisible by m. That is, m is a factor of b of t minus a of t, or m divides b minus a. So if you look at the definition of congruence modulo a natural number in Z, it's the same exact definition. Okay? We just copy and paste it directly over. Right? So this is not new, which shouldn't be new. So I won't like go into a bunch of examples right now, but we will start proving things about it. So our first result is that addition is well defined. That's how you should think about this. So plus is well defined. Mod m. That means that if a1 is congruent to b1 mod m, and a2 is congruent to b2 mod m, then a1, addition, I'm also doing multiplication, sorry. Addition and multiplication are well defined. Then a1 plus a2 is congruent to b1 plus b2 mod m, and a1 times a2 is congruent to b1 times b2 mod m. Cool, great, fantastic. All right, proof. Okay, so we are going to start by writing out what our hypotheses mean. So by hypothesis, a1 is congruent to b1, so a1, or it doesn't matter the order we do it, but I guess I'm going to be consistent with what I wrote up there. b1 minus a1 is divisible by m, so it's m n1 for some n1. And b2 minus a2 is also divisible by m, so that's m n2. Then a1, or let's see, I think we can jump straight to addition now. Then, okay, so now we have to look at this guy. And what does it mean for them to be congruent mod m? It means the difference of the the right term minus the left term is divisible by m. So let's look at b1 plus b2 minus a1 plus a2. We need to show this is divisible by m, but we can factor that negative in and then reassociate as b1 minus a1 plus b2 minus a2. And then we'll go ahead and we'll plug in our expressions for both of those. All right, and then we can factor out that m. Cool. So what do we have here? On the left-hand side, we have the difference we were looking at to prove congruence mod m. And on the right-hand side, we have is a multiple of m. So we can conclude from this then that a1 plus a2 is congruent to b1 plus b2 mod m. And if you go back and you look at like all these proofs for z mod n that you learn in number theory or whatever, it's the same proof, only technically I should be writing of t here, but if we wrote of t everywhere, it would just get kind of bogged down in the notation. Right? Okay, so that's this guy. Now we have to do this one. And I believe this one we do a trick. So let's see. We have a1 times a2 is congruent to b1 times b2. So let me say for multiplication, we need to look at b1. I'll put a colon here. We need to look at b1 times b2 minus a1 times a2. Right, that's the relevant difference. And then we're going to insert 0. So we're going to say, hey, b1 b2 minus b1 a2 plus b1 a2 minus a1 a2. Is that good? I think that's good. So I've effectively input a 0 there, right? So we haven't changed anything. We can go ahead and factor out a b1 on the left from the first expression, and then an a2 on the right from the second expression. And now these are guys that we can substitute. So let's go in and substitute those. All right, so b2 minus a2 is mn2, and b1 minus a1 is mn1. All right, we have a commutative ring, so we can pull out m's wherever we want. I'm going to pull them out on the left of both terms. And that does it, right? I guess I shouldn't end the proof just yet. So on the far left-hand side, we have the relevant quotient we wanted to look at. And on the right-hand side, we have a multiple of m, or the relevant difference, not the quotient. On the right-hand side, we have a multiple of m, so what must be true? Well, a1, a2 is congruent to b1, b2 mod m. All right, so what this is telling us then, that's the end of our proof. This together with a bunch of things that we already know about rings is telling us that the set k of t mod m of t, which is just notation for congruence classes of polynomials mod m. So we regard two polynomials as the same if they're congruent mod m. This is actually a ring. It's a commutative ring. Commutative, again, like we discussed in class, refers to the multiplicative structure. Addition is always, 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 always commutative. And we're not going to go through the ring axioms because, well, maybe I'll look at your homework assignment for this chapter and maybe I'll assign it. But there's no, you've seen the proof of this before. You had to have to get into this class. But you should be comfortable with going through and checking that the ring axioms indeed hold, and this is in fact a ring. It's not in general going to be a domain, which I'll give you some examples in the next few videos. So this should at least bring back some memories, and you should really think of. I personally like to think about this as just z mod n said differently. Well, in the setting of polynomials. They're very similar because they both share a lot of algebraic properties. So it's helpful to like think back, like, oh, what do I know about z mod n? That's probably true here.